So let's talk about sublimation. Sublimation is the transition from a solid directly to a gas without passing through the liquid. So here we have an illustration of an ice cube. Solid water, the molecules have energy. They vibrate. The average kinetic energy is related to the temperature, but some of the particles have higher kinetic energy than others. Some of them have enough energy that they can break loose. So if you have some on the surface that have enough energy to break loose, they can go into the gas state, and that's known as sublimation. It'll be the atoms that have the higher thermal energy. So a solid can sublime. Now, this doesn't necessarily happen at a very significant rate, but it can happen. So even solids have a vapor pressure. It's usually really low, so low that it doesn't matter, but solids have vapor pressure. The opposite of sublimation is called deposition. That's going from a gas directly to a solid. Can't remember what's next on the slides. Yeah. So sublimation will usually occur faster in an open container because those molecules that escape into the gas state then can escape. And this accounts for several things that you might observe in your freezer at home. Ice cubes that are left in the freezer for a long time slowly shrink. It's not necessarily that there's something wrong or someone's messing with your ice cubes. But they'll just get slowly smaller and smaller and smaller because they're subliming. And so they're going into the gas state. So this also causes buildup of frost. Now modern freezers have defrost cycles and keep this from happening, but older freezers and little dorm fridges, the ice just builds up. I was in a motel recently that had a little fridge, and obviously it was on all the time. The freezer was so full of frost that you couldn't even put anything in there. It was just like completely frosted over. Some of that is due to water subliming, so ice cubes subliming. Some of it also, a fridge like that gets opened a lot, and so then air with humidity in it gets in there, and then that'll freeze up. Ice crystals will grow inside of airtight bags of frozen foods. I've always noticed this with like frozen French fries and tater tots and things. You buy them because it seems like a really great idea, and then you stick them in the freezer and you kind of forget about them, and then someday you're like just desperate for something to eat, and you're like, oh, tater tots, okay. You open it up and you dump it on the pan, and there's all this ice crystals. Like, why do they pack all these ice crystals in here? Don't they know that this is going to melt in the oven and get everything all wet and soggy? They didn't put those in there. That happened because I forgot about them in the freezer. That water used to be inside the tater tots, and it has slowly sublimed out of them. The bag is sealed so it can't go away, so it bounces around and gets cold, and then it freezes again and it forms little ice crystals. Well, you lose enough water that way, and then the food's not going to be very good anymore. We call that freezer burn. It has nothing to do with burning, but it gets dehydrated because the water sublimes out of it. One thing you can do there's two things you can do to counteract that. You can use a deep freeze. The colder the freezer, the less sublimation occurs, or you can seal the food without any airspace. So you can use a vacuum sealer or wrap the meat tightly in foil, which will conform to the contours of the meat, and then put it in a Ziploc bag and get as much air out as possible. That'll help protect your food. Dry ice is relevant to sublimation. So here we have a photograph of dry ice. Dry ice is a lot of fun. It's solid carbon dioxide. It's called dry ice because it doesn't melt. Regular ice, I guess, would be wet ice, right? It melts and it gets everything wet. Dry ice doesn't melt. It sublimes. What we see here, as it looks like all these vapor trails coming out, that is colder air. It's the cold temperature from this It's cooling the air, and then we see the water vapor condensing. But dry ice just sublimes, it disappears. Remind me, and I'll tell you a story about my husband as a boy, dry ice in a giant pickle jar. Fusion. So fusion is melting. Melting or fusion. So we're going from a solid to a liquid. Freezing is the opposite, liquid to solid. So fusion doesn't always bring up the idea of melting. But think about chocolate chips. Chocolate chips are solid, right? And if you heat them, what happens to them? They melt and they fuse together, right? And then you've got this big mass of chocolate. So fusion is melting. You take a block of ice and you heat it up, the molecules vibrate faster as the temperature goes up. At some point, the molecules are going to have enough thermal energy to partially overcome the intermolecular forces and move relative to each other. They may not have enough to escape. Some of them will, but most of them won't. But they have enough energy to partially overcome the forces and slide around, so it becomes a liquid. So we see a similar heating curve to when we were boiling the water. Here we're starting at negative 10 degrees Celsius, so this is a solid ice. And as we heat the ice, it gets warmer until it gets to the melting point at 0 degrees. At this point, all of the energy that we're adding here goes into breaking those intermolecular forces and turning it into a liquid. And the temperature will not rise until all of the ice has melted. Once the ice is melted, you add more heat, the temperature will continue to go up. This is very useful because if you have a mixture of ice and water, you can be pretty sure that that temperature is very, very close to 0 degrees Celsius. And I believe that's why it was defined as 0 on the Celsius scale. 100 on the Celsius scale is the boiling point of water. If you've got a pot of boiling water, the temperature is going to be extremely close to 100 degrees Celsius. So you don't need any technology to create 0 degrees or 100 degrees Celsius. If you add more heat, you'll melt it faster, but you will not increase the temperature. So melting is an endothermic process. That makes sense. We need to put energy in to melt the ice. So the energy required for that is called the heat of fusion. Not sure why we don't call it the heat of melting, but maybe that just doesn't sound fancy enough. It's the heat needed to melt 1 mole of a solid. So here we've got solid water going to liquid water. Heat of fusion is 6.02 kilojoules per mole. That's significantly smaller than the heat of vaporization. Heat of vaporization requires that we break all the intermolecular forces. Here we just need to partially overcome them. So melting is endothermic. That means that freezing is exothermic, and the same amount of heat is released. So as I was driving to work this morning, I saw the wind machines. Well, I heard the wind machines at home. Where I live in Reedley, there's a lot of citrus fields. And when the temperature drops below freezing, it damages the trees. It damages the fruit. So what the farmers will do is they'll water the fields, they'll flood them, and that protects the citrus because as the water freezes, it releases heat, which prevents the temperature from dropping further. Because as long as you have ice and water together, the temperature is 0 degrees Celsius or 32 degrees Fahrenheit. The citrus is okay until it gets down to around 26, 27 degrees Fahrenheit. If it stays that way for like 4 hours or so, you're toast. So if they can keep it at 32, everything's fine. So they flood the fields, and then they've got these big wind machines that sound a lot like helicopters going all night long, and they blow the air around because you need to circulate the warmer air from down where the water is up and around. And so here we have heat of fusion saving your oranges. Heats of fusion generally much less than heats of vaporization. I mentioned this earlier because you're only partially overcoming the forces. So here's a bar graph showing the difference here. So blue is fusion, red is vaporization. So heats of vaporization a lot higher. And again, we just look up these values. In a table like this, we don't memorize these things.